Please let me know my screen is visible to you all. Am I audible and my screen is visible?
Yes, sir.
Great, great. So I'm audible as well as my screen is visible. So I will go ahead with today's session. So as you all know, yesterday we have already discussed about integration, various form of integrals, line, surface, and volume. We have also discussed about gradient, divergence, and curl. We have also given a brief description about Stokes theorem and divergence theorem. And we have also discussed about Laplace equation. That was the last thing what we discussed yesterday. And due to connectivity issue, we have stopped over review of complex number. So I would like to say that review of complex number is very important from the perspective of electromagnetic theory, because as I have already said, everything is complex in nature. So whatever quantity we have, it has some sort of real part and some sort of imaginary part. So today I will quickly finish the complex number, and then we can go ahead with fundamental definitions of electrons, magnets, and all sort of fields. So as you all know, yesterday I have already discussed about this too, but I will brief it out. So complex number is something which has a real part and imaginary part. Example of a complex number is impedance, which has resistance and reactance. Resistance is most effective. Reactance is nearly less effective. Or concrete effect is due to the real part, and subconcrete effect is due to the imaginary part. So that is what the real number is. Fundamentally, we say Z is a real number, which is x plus minus jy. So either plus or minus, where x is real part and y is imaginary part. So we can say x is real part of Z and y is imaginary part of Z. So in trigonometric functions, or you can use trigonometry for writing it into rectangular to polar form. So if a number is Z, which is equivalent to x plus minus jy, then it can be written as mod of Z cos theta plus j mod of Z sin theta. It is magnitude of Z cos theta plus j sin theta. And it can also be written in alternative polar form, where I write it in terms of magnitude and e to the power j theta, where theta is the angle which z makes with the x-axis. In the next slide, I will show it how it is. So suppose if I have a complex number z, which is having this type of orientation, and it is making theta with x-axis, as you all can see. So if I write z in terms of x and y component, y axis is imaginary axis and x axis is real axis. So if I say projection of z over x, then x is equivalent to mod of z, whatever the concrete value of z we have, into cos theta, because projection is in horizontal direction. And if I say y, then y has projection, z has projection in over y direction, and y will be equivalent to mod of z sin theta. So in this way, I can write real part and imaginary part in terms of the angle which this complex number makes with x-axis. Mod of z can be written as root of x square plus y square, whereas theta is equivalent to tan inverse of y upon x. So this is how you can write a complex number with respect to theta and also with respect to the projection of z over x and y. I hope this is very simple and everyone knows about it. So how we have done it? We have used Euler's identity, where e to the power j theta is equivalent to cos theta plus j sin theta. So if I write g equals to mod of e to the power j theta, then it is nothing but the same value what we have written in previous slide. So the relationship what we have developed, it comes from here, where x equals to mod of z cos theta and y equals to mod of z sin theta. Just a minute. Hello? Tell me. actually. Okay, done. I will do it. Yes, yes, correct. I will do it. So just give me 1 minute. I have to start recording, but I don't know from where I have to start recording. If it's here. Okay, so this is so in my where to get recording. Um, okay, so recording has started. I can now go ahead with the presentation. Sorry for the interruptions. I hope still I am audible and my screen is visible to you all. So I have already said that a complex number can be projected in x-axis and y-axis, where x-axis denotes your real part and y-axis denotes your imaginary part. So this is done using Euler's identity, which I have already explained. Now there is one important concept which is known as conjugate of a complex number. We call it as complex conjugate of a complex number, which is denoted by g to the power asterisk. Generally, if I have a complex number, which is denoted by x plus minus jy, then if I revert the sign, then I will get the complex conjugate of it. It is very important because when I take,
Sir, your is
please,
not visible.
screen is not visible.
Yes, sir.
Okay, I'll share the screen then again. Some issues. Okay, let's see. I hope now screen is visible.
Yes, sir.
Right, great. Now I will go ahead with this. So complex conjugate is very important, as I already said, because when I take product of the complex number with the complex conjugate of the same number, then I end up getting a real number. That is very, very important because when we perform division of a complex number, that in the denominator we require a real number for ease in calculation in mathematics. So if I have a number or I have to divide two complex number, I can easily make the denominator as real number by simply multiplying with the complex conjugate number with the numerator and denominator. So that is very important. And in real world also, complex number and complex conjugate number are known as dual of each other. Any number which is having a real part and the imaginary part will always have its complex conjugate number, and on multiplication of that complex conjugate number with the complex number itself will result in the real part. That I will show you how it is. So let us start with the theorem of equality. Two numbers, suppose in this case z1 and z2 are two complex numbers which have x plus jy1 and x2 plus jy2, then these two numbers are equal or equivalent if and only if x1 is equivalent to x2 and y1 equals to y2. Or if I talk in terms of polar form, then magnitude of z1 should be equivalent to magnitude of z2 and theta 1 should be equivalent to theta 2. So that is how two complex numbers will be equivalent. If any one of the property is not fulfilled, then this particular two numbers cannot be equal. The equality theorem says that real part should be equivalent to the real part, imaginary part should be equivalent to imaginary part, then only these complex numbers are same. And if it is written in polar form, then both magnitude as well as angle should be same. Then only we can say that two complex numbers are equivalent in nature. So that is what equality theorem says. Then addition and subtraction. I hope everyone knows how addition and subtraction is performed. In complex case, generally real part is added and subtracted and imaginary part is added and subtracted. I have taken two examples of addition and subtraction. Z1 and Z2 are two complex numbers with real part as A and X and imaginary part as B and Y. You can see how addition is performed. X1 plus Z1 plus Z2 is equivalent to A plus X where a plus x is the real part of both the numbers, and b plus y, where b and y are the imaginary parts of this number. Similarly, if I perform operation of z minus z2, then I get it as a minus x and b minus y. So this is how you can perform addition and subtraction of two complex numbers. Then we can also perform multiplication of two complex numbers. So z1 and z2, suppose they are two complex numbers. Then you can see how we have performed the multiplication. In case of polar form, it's much easier, because if it is written in polar forms, then simply add these two thetas, and we can have product of magnitude of z1 and z2. So this is how multiplication is performed when we multiply two complex numbers. I hope these, I'm just making it fast because I know mostly everyone knows about these fundamental concepts, and you know how to multiply two complex numbers, how to add and subtract two complex numbers. As I was saying, in case of division of two numbers, when z is not equal to 0, so please remember, I'm talking about two numbers which are not equivalent to 0. So if I perform division, that is z1 upon z2, where z1 is x1 plus jy1 and z2 is x2 plus jy2, then if I have to perform this division, then you see how I have multiplied denominator and numerator with the complex conjugate of the denominator. So x2 plus jy2 is the complex number in denominator, and I have multiplied this numerator and denominator with the complex conjugate of the denominator, which is x2 minus jy2. And then I have performed the operation. And on final product, we get denominator as real number. So when I get denominator as real number, it's very easy to write the complex number in terms of real part and imaginary part. Suppose if I have at the bottom x minus jy2, x2 minus jy2, then the complex conjugate becomes x2 plus jy2. Simply changing the sign gives you the complex conjugate of that particular number. So as I have already said, for division of two complex numbers, this particular complex conjugate is very, very helpful, because it ends up giving denominator as the real part or real value of the denominator we get. And that is very important when we have to write the final product in form of complex number. If I write the final product, then this value upon this value upon this value will be the real part, and this value upon this value will be the imaginary part. So final z1 upon z2 can be written in terms of real part and imaginary. In case of polar form, it is much easier to do the division. As you can see, suppose z1 and z2 are two complex numbers. So magnitude of z1 upon magnitude of z2, both are real, and we can subtract theta 1 from theta 2 from theta 1. So I can write it as a e j to the power e to the power j theta 1 minus theta 2. Using Euler's identity, I can write it as cos theta 1 minus theta 2 plus j sin theta 1 minus theta 2. So this is how you can perform division of two complex numbers. If you see it carefully, it's very easy to perform these operations when we have written these complex number in polar forms. So writing complex number in polar form is often very easy, and mathematical operations performed on polar forms of complex number is much easier as compared to the rectangular form. As you can see in our previous slide, this much calculations is involved. So a huge amount of calculation is involved when we write division of z1 upon z2, and in the case of polar form, simple subtraction of theta 2 from theta 1 will suffice the purpose. It depends upon the person which form of complex number you are denoting and which form suits you. Sometimes writing in rectangular form is much easier. Sometimes writing in polar form is much easier. And depending upon the person to person, you can perform the operation. But please remember, in all cases, it is always possible to convert from rectangular form to polar form and from polar form to rectangular form. So that depends upon the person who is doing the operation, whether you want it in polar forms or in rectangular form. So this is how you can do division. Now you know power of integers can also be included. So if z to the power n is there, then this complex number can be written as mod of z e to the power j theta. This is polar form of the complex number z. So if I give power over here, then it can be written as mod of z to the power n, and it goes to power of j theta. So it is e to the power j n theta. It can be written as mod of z to the power n, and using Euler's identity, I can write it as cos n theta plus j sin theta. And also, if I write in terms of n equals to half, then I get up with this. So mod of z to the power half, e to the power j theta by 2, because now n is half, it comes as theta by 2. Using Euler's identity, I can write it as cos theta by 2 plus j sin theta by 2. So this is how you can denote powers. There are some useful theorems. Please remember these theorems, because these theorems are fundamentally used when we solve complex numbers and when we perform operations using complex numbers. So I hope these are given in standard mathematical books. For standard classic mathematics books, you can find these identities and relationships, and you can use these when you perform operations on complex numbers. So I hope complex number is very clear. It was just to brush up your concepts of complex number, that how you will use the complex number and what are the various possible operations that can be performed using complex number. So if I ask you which form of complex number is more suitable for performing operations, then what should be your answer, and what could be the possible way by which you can do this? So in audience, if someone can tell me which form of complex number is easier for mathematical operations. If I am audible, then please someone can come up and say me that which particular form of complex number, rectangular or polar.
In multiplication and division, polar is better, and
Yes.
subtraction and addition, rectangular is better.
Right, correct. So see, depending upon the person, you can go for rectangular and you can go for polar. Generally, polar form is well recommended for multiplication and division, and for addition and subtractions, we recommend rectangular coordinate system. So again, I'm not saying this is the hard and fast rule. You can of course go with polar form for performing addition and subtraction. Even you can perform multiplication and division using rectangular form. But for ease of our calculations, we go with these concepts, and then we can use multiplication and division for polar form, and for addition and subtraction, we can use rectangular form. So I hope you all have now fundamental knowledge of all sort of mathematical operators we use. So let me revise. Quickly, I will tell you what we have done. So we started our lecture 3 days back with vector calculus. From vector calculus, we started with coordinate system. We have seen 3 fundamental coordinate systems, namely Cartesian coordinate system, cylindrical coordinate system, and spherical coordinate system. After that, we have seen integration. So we have seen line integral, surface integral, and volume integral. After integral, we went to gradient, divergence, and curve. And after going to this curl and all, we went to theorems, Gauss theorem, divergence theorem, and Stokes theorem. Then we went to complex number. So this is all mathematics which is fundamentally required when we do calculations for electromagnetic field. So I quickly want you that if you have any queries, please ask regarding all those concepts we have done in form of mathematical operators. If you have any queries, please go ahead. Otherwise, from today onwards, we will be starting electromagnetic theory, field theory, which is very important. And this entire field theory will be analyzed using all those operators which we have seen in last 3.5 days. So if there is no question, then I can go ahead. I hope the concepts were crystal clear, and I'm very sure that many people would have got those. Any issues, then I can entertain the issues, or I should go ahead. So I hope everything is very clear. Either it is very clear or I don't know, but for the time being, let me consider that whatever is being discussed in last 3.5 days is crystal clear to everyone, and you know the fundamental concepts of mathematics which will be used in electromagnetic field. So assuming that now you know everything about the mathematical operators which we will use in analysis of fields and theories, I will go ahead with explaining the parts of electric field, electrostatics, then magnetostatics, then finally I will go to electromagnetic waves and particles. So now from this day onwards, I will pick up with electrostatics, magnetostatics, and electromagnetic fields and waves. So let's start with those. So I will start this electrostatics and magnetostatics with two fundamental parameters. First is permittivity and another is permeability. So when I say permittivity, it describes how an electric field affects and is affected by a dielectric medium. So there is suppose some sort of medium. It may be dielectric, it can be magnetic, it can be free space. So how an electric field will be affected when we have a certain medium with certain dielectric properties. Now this type of property is known as permittivity of the medium. It is the inherent property of the medium which cannot be changed. Please remember this. It is the inherent property of the medium which cannot be changed. For example, we have vacuum. You all may be knowing that vacuum is something where we have nothing, or emptiness is known as vacuum. The place where nothing is there is vacuum, and we also call it as free space. But still, free space has an inherent permittivity of 8.85 into 10 to the power minus 12 farad per meter. So this is the lowest possible permittivity of a medium, and this is of free space. Now, all other materials have different permittivity, and we can relate the relative permittivity of that particular material with the permittivity of free space. So, relative permittivity of the material ER multiplied by E naught, epsilon R into epsilon naught gives you the actual permittivity of that particular material. Now, generally, permittivity is for materials which have dielectric constant. Dielectric constant, it means it is giving you the fundamental property of the material which resists electric field to pass through it. If it has a very large permittivity, then electric field cannot pass through it, and the amount of loss in electric field will be larger. So this is what permittivity is. We will be using this concept of permittivity when we solve Maxwell equations, when we solve fundamental concepts of electric field, and vice versa. Now the second parameter, which is again I already said, this is also very important. This is known as permeability of the material, and it fundamentally is defined as the degree of magnetization of a material that responds linearly to an applied magnetic field. So permittivity is something related with electric fields. Magnetic permeability is something related with magnetic field. So they are dual in nature. I have electric field and I have magnetic field. Ease of passing of electric field can be defined in terms of permittivity, and ease of passing of magnetic field can be defined in terms of permeability. So the same importance which permittivity have in electric field, permeability have in magnetic field. The value of permeability in free space, or we call it as vacuum, is mu naught, which is 4 pi into 10 to the power minus 7 Henry per meter. So this is the lowest possible permeability of a material, and this is of free space. Now, many materials have permeability of epsilon mu naught, except for ferromagnetic material, such as iron, where it is very large. So, if we talk about general materials, such as air or all other materials, we can say FR4, Rogers, or all these type of materials, permeability is mu naught, epsilon naught, mu naught, which is 4 pi into 10 to the power minus 7 Henry per meter for most of the materials. But still, there are some materials which are ferromagnetic in nature, such as they get attracted to magnetic fields. And you know, iron gets attracted to magnet. So iron has permeability very, very large. If I am correct, then permeability of iron is greater than 10. So such type of material will behave in magnetic field in a different fashion. But mostly, or most of the materials in the modern scenario are the materials which are inherent to permeability and which has their permeability as that of free space. It means they are not affected by the magnetic fields at all. So we can say relative permeability of a material, that is mu r equals to mu upon mu naught, where mu naught is permeability of free space and mu r is the relative permeability of that particular material. This is what permittivity and permeability is. Now, permittivity and permeability gives you an understanding about electric field and magnetic field propagating in a particular medium. And if you recall the formula of speed of light in free space, it is given as C equals to 1 upon root of mu naught into epsilon naught, which gives you the value 3 into 10 to the power 8 per meters per second. So speed of light in free space is also defined in terms of permittivity and permeability of the material. So very standard definition of permittivity and permeability I have provided, and the speed of light, or you say speed of electromagnetic waves traveling in particular medium, depends upon the permittivity and permeability of that particular material. In free space, I have already given you the values. So in free space, these values gives you speed of light, which is 3 into 10 to the power 8 meters per second. But in different medium, this velocity will change because this is the least possible permittivity and permeability. In other mediums, the value will be higher. And since value will be higher, and they are in the denominator, the speed of light, or you call it as speed of electromagnetic wave, will be less as compared to the speed of light or electromagnetic waves in free space. So please remember, highest possible speed of electromagnetic waves is in free space, that is 3 into 10 to the power 8 meters per second. For all other mediums, since permittivity and permeability will be larger, we can say speed of light will be less in all those particular mediums. So please remember these two concepts of permittivity and permeability. If any issues of that, please do ask. So it's open for the questions. You can pop up your questions if you have any issues. So no questions? Are you all listening this? So I want some responses, otherwise I think that no one is listening and I'm just talking to the walls.
Yes, sir, we are getting the point, sir.
Yeah, you're getting it now, so then I can go ahead, right?
Yes, sir.
Great, fine, great, great, great. So, so I hope this concepts of permittivity and permeability are done. Now let me move ahead with electric fields and magnetic fields, electrostatics and magnetostatics. So I will start with that now. So this is going to be day 4. So I hope my screen is visible. Wait, let me share it first. Okay. So actually, today I would have to start from this particular slide, but yesterday we missed some part of our slides, so I have continued with those slides. So from this day onwards, I will have an understanding that all mathematical operators, what are taught to you has been covered, and you are very confident about all those operators which I have used. I will not discuss about those operators in the coming slide. I have an understanding that everyone knows those fundamental concepts of mathematical operators, and we will use those fundamental concepts in electromagnetic theory and waves. So with this understanding, I will start my session for electromagnetic waves and theory, which has nothing to do with now mathematical operators, what we have already dealt with. I have an understanding, you know this. If someone is saying something, then please pop up and say, otherwise I can continue. Right. So today's agenda consists of 5 parts. The first part is electrical charge. So we will review some things you hopefully learned in your high school. Then we have Coulomb's law, which is electrical force between charged particles. Then you must be able to calculate the electrical forces between one or more charged particles. That is what we have to learn in terms of Coulomb's law. Then we will deal with electric field. You must be able to calculate the force on a charged particle in an electric field. That is what you must get from the electric field concept. Then electric field due to point charges. So you must be able to calculate electric field of one or more point charges. That is what you must get from this particular topic. And the last topic, which is charged particle in a uniform electric field. And in this, you must be able to solve the trajectory of a charged particle in an uniform electric field. So that is what we will cover today. So I will address one agenda at a time. And after every agenda, we will try to do some calculation so that it makes very clear that what we have learned, we are able to apply that concept in the real world and in the real time. So let's start with the first topic, that is electric charge. So the question arises, what is electric charge? So when you say electric charge, you would have witnessed many phenomena which relates to electric charge, such as if you rub a plastic scale on your hairs and you keep it near the fur, then fur gets attracted. This is very common phenomenon, and I'm very sure every one of you would have done such type of activities when we were in our first or second class. So that is our understanding, and that is because of some charge. Because of that, fur gets attracted to the scale. So humans cannot directly sense the charge, but some animals can. This is also our understanding. We cannot directly sense it. Sense it means I cannot see it, whether their charge is there or not. But some animals have these fundamental properties, such as you would have heard about owl, which is able to see in the night, and there are many other animals which can see charges or which can actually sense the charge. Now we can absorb charge indirectly via its effect on matter. That is what we can see. As I was saying about a scale, if I have a scale, I rub it on my hairs, and that scale, if I bring near to the fur, then I can see, yes, there is a charge, and that charge is acting some amount of force, whether attractive or repulsive, over that particular scale, and fur gets affected. So that particular force will be attractive in nature. So Q, small q or capital Q is the fundamental symbol I will be using in my entire presentation. And unit for charge, which I will refer to, will be Coulomb. So this is what charge is. If I denote Q or capital Q, then please consider it as a charge or unit charge, and the unit of this will be Coulomb. So if you talk about the known universe, there are two types of charges, positive and negative. And we have this understanding that like charges repel each other and unlike charges attract each other. So if I say I have a positive charge and I have a negative charge, then positive charge will attract the negative charge. And if I have positive charge and positive charge, then two positive charge and two negative charge will repel each other. I have indicated the arrows. So if I say for the first two positive charge, they are repelling each other, they are in opposite direction. Same is true for two negative charges. You can see if I have one negative charge over here, another negative charge over here, then both the charges will repel each other. Contrary to this, if I have a positive charge and a negative charge, then positive charge will attract the negative charge. So this is our understanding about the charge, that positive charges attract each other and negative charges repel each other. So there is one fundamental law, that is law of conservation of charges, that says net amount of charge does not change in any process. Please remember this. The net amount of charge, whatever the amount of charge is there in a particular system, and it goes through a particular process, or some work is done over here, whatever work is done over here, but the net amount of charge on that particular system won't change. And if charge changes, the entire philosophy behind physics will change. The law of conservation of charge is very important. It says that net amount of charges does not change in any process. Any process means any process. Whatever process you do for a particular system, but net amount of charge in that particular system will be constant. Constant, or it will be balanced. Balanced and stable will be an appropriate word to say, because balance means positive and negative are balanced. So with this understanding, charges are quantized, comes in unit, and generally the smallest possible unit of charge is, that is of electron, and the value of this is 1.6 into 10 to the power minus 19 coulombs. So this is the smallest possible charge what we know till date. That is of electron, and that is very less. It is 1.6 into 10 to the power minus 19 coulombs. So there are three elementary particles that you already know from your classic physics. There is protons, neutrons, and electrons. We generally indicate protons as positive charge. So the positive charge of a proton is 1.6 into 10 to the power minus 90, and that of electron is minus 1.6 into 10 to the power minus 90. And we have neutrons. These are uncharged in nature, so we don't have any particular charge in this. I have given you an example of helium atom. You can see there are two protons, two electrons, and two neutrons. So there are two neutrons which have positive charge, which is equivalent to 2 into 1.6 into 10 to the power minus 90, because we have two protons. One proton has this charge, another proton will have the same charge. Similarly, if you see there are two electrons in an atom of a helium, then these two electrons will have the charge of an electron. So this will have twice the charge of electron. If you look at this particular atom, you can see that the total positive charge is equivalent to the total negative charge. Or we can say that the charge of electrons is equivalent to the charge of protons. Now, as I already said, that positive charges attract negative charge. So this positive charge of protons which is equivalent to the total negative charge of the electrons, will attract with a larger force. And due to this, these electron gets bounded to protons, and we have a very stable geometry. Electrons cannot move out of the helium atom. So it is very important that an atom has a balanced charge. If it doesn't have a balanced charge, then atom becomes an ion. It has some sort of positive or negative charge. In this case, it is completely balanced. Amount of positive charge is equivalent to amount of negative charge. So it is very, it is the same scenario which takes place in mostly all of the atoms. All atoms, as you all know, that number of protons and numbers of electrons are equal. So that every atom is stable if it has same number of electrons and same number of protons, and the charge is conserved in nature. So both electrons and protons have the same charge, and the atom becomes stable. So for the stability, this is also an essential criteria that number of electrons and number of protons should be same in a particular atom. So that is our understanding of a charge. Now any charge, suppose we have a large charge, large source of charge, even that particular charge can be quantized in terms of electron. We sometimes denote charge in terms of Coulomb and multiple of electron. For that particular thing, what we do, suppose I have a large source of charge, then I will discretize that source into small fragments, and that small fragments can be further discretized into further smaller fragments until the level of electrons, and then on the basis of those electron charges, we can count, or we can have an algorithm that we have this many number of electrons, and that will be the total charge over that particular object. So charge is described or quantized in terms of electrons. So electron is the fundamental building block which refers a charge. And the value we already have known from our experiments, that charge on the electron is minus 1.6 into 10 to the power minus 9. That is negative in nature. So please remember this. So once you know the electric charges, now let us go to Coulomb's law, and it says what is the electrical force between charged particles. So now you understood what is charge. Now from the knowledge of the charge, let us try to say what type of force is between two charges. So let us see what it says. Suppose we have two charges. I have denoted Q1 and Q2, and I have also denoted the directions Q1 and Q2. Please remember, in this case, I am talking about positive charge. So Q1 is positive and Q2 is positive. So you can see the direction of this force is opposite to this. So if I say F12, then this is the force exerted on 1 because of 2. So I have two charges, Q1 and Q2. Q2 will exert or impose some amount of force on Q1, and Q1 will also impose some amount of charge on Q2. But since both charges are same, equal 2-point charges I have considered, Q1 and Q2, so the amount of force exerted by 1 on 2 and by 2 on 1 will be exactly same. So magnitude of F12 and F21 will be same, but both will be in opposite direction. As I have indicated, force of 2 on 1 is in this direction, and force of 1 on 2 is in this direction. So in terms of magnitude, both forces will be same, but in terms of direction, the forces will be in reverse. That is what it's clear from this particular diagram. So the distance between the two forces, let me consider it as R12. That is the radial distance between two charges. So if I calculate the amount of magnitude between these two charges, it is given by the formula F12 is equivalent to K magnitude of Q1 Q2 upon R12 square, where Q1 Q2 are charges, point charges, R12 is the distance between the charges, and K is 1 upon 4 pi epsilon naught. Please remember, 1 upon 4 pi epsilon naught. In many standard books, you will find out that instead of using K, they have written it as 1 upon 4 pi epsilon naught, where epsilon naught has the same value I have explained when I was talking about permittivity, which is 8.85 into 10 to the power minus 12. But instead of using epsilon naught, I prefer using K, because K gives you the final value as 9 into 10 to the power 9. In many complex calculations, it becomes very tedious to evaluate every time 1 upon 4 pi epsilon naught. So instead of evaluating 1 upon 4 pi epsilon naught, I can directly use K is equivalent to 9 into 10 to the power 9 Newton meter square upon Coulomb square. So this is what we can do. And force between two charges exerted, one will exert on other, and other will exert on the first. That we can find out from this particular formula. I hope someone is popping some questions. Let us see. No, there is no question here. So force between two charges Q1 and Q2, generally point charges. Please remember, I am talking about point charges because Coulomb's law is applicable in point charges. So we have 2 point charges Q1 and Q2, and the force between these 2 point charges, or force on 2 because of 1 or on 1 because of 2, we can find out with this relationship, which is known as K magnitude of Q1 Q2 upon R12 square. Please remember this. This is very important. So let's go ahead. Okay. So this is an official starting equation. When I say official starting equation, F12 equals to K Q1 Q2 upon R12 square, where I am considering two charges, Q1 and Q2. R12 is the radial distance. So official starting equation means an equation which we consider as a fundamental law. We don't go with the derivation of this particular equation. So when I say it is an official starting equation, students or the researchers can directly start with this equation. We call it as fundamental starting equation, where proof is not required. Because Coulomb has already proved this, we never look for the proof, and this particular equation we can use directly as it is. So official starting equation can be used without deriving them, as I have already said. All other steps of a solution should be need to be derived. So suppose if you're doing a mathematical calculation and you need to use this particular equation, then of course you can use this equation. But after all calculations after this equation should be derived individually, because this statement can be true, but rest of the statement which comes after this equation may or may not be true. So we must be very careful after using the starting equation. Whatever other operators or operation we perform, that has to be derived carefully. So there could be different possible use of this particular equation. For example, generally we refer this equation as Fe, that is force. E can be on 1, 2 or 2, 1 or different charges. K has the same meaning, which is a constant. QAB, where A is first charge and B is second charge. We can reverse this also. So we can write it as A is second charge and B is your first charge. And D is nothing but the distance between these two charges. So this is more generalized form of Coulomb's law, where I have written in terms of two charges, QA and QB. D is the distance, and K is the value, that is 1 upon 4 pi epsilon naught. Now when I say starting, it does not mean that the starting equation has to be the first thing that appears on your paper. Starting equation here I refer to that this particular equation can be directly used. Please don't recommend this equation as the fundamental starting equation that every time you have to start with it. The concept of starting equation over here is that this equation can be directly used without further proving it. You can write it as per the Coulomb's law, and then you can use this equation. So that is what the Coulomb's equation is, and that is what Coulomb's law is. Now, some fundamental theory behind Coulomb's law. So Coulomb's law is strictly valid for point charges only. Please remember this. You cannot directly apply Coulomb's law in another particular principle where larger sources are there. It is only used when very small amount of charge is there. It is a good approximation for a small uniformly charged object. So I have given you these two charges. So I have two charges, one over here, another over here. R1, 2 is the distance. So in this way, you can use Coulomb's law in 2 point charges. But suppose if more than 2 charges are involved, then the net force is the vector sum of all forces. Please remember, if more than 2 charges are involved, then what will be the force? The force will be the vector sum of all forces, and this can be referred as superposition theorem from our classic circuit theory, what I hope everyone has gone through. Now for objects with complex shape, you must add up all the forces acting on each separate charge. So that is what Coulomb's law will be applicable. Suppose I have 2 plates, then individual effect should be studied. Suppose I have this plate with 3 charges, we call it as 3 elements, and 3 elements over here, then this particular thing should be discretized into small points, and then individual force should be calculated. That is what our requirement is. So for calculating the charge, for calculating the force between 2 charges, we have to be very sure that the amount of charge is continuous and the amount of charge is in a point form when we use Coulomb's law. So that is very important to understand, and please remember this, that Coulomb's law is strictly applicable for point charges only. So I have a quick question for this, where I say as applicability of Coulomb's law. It says I have a positive charge Q1 plus Q is located at a distance d along the y-axis from the origin. What I'm saying, I have a positive charge Q1 that is plus Q, and it is located at a distance d along the y-axis from the origin. We have a second positive charge that is Q2 is located at the origin, and we have a negative charge Q3 whose value is minus 2Q, and it is located on the x-axis at a distance of 2d from Q1. Calculate the net electrostatic force on Q1 due to the other 2 charges. So if everyone is there, question is very clear to everyone?
Yes, sir.
Yes, great. So I will try to solve it using Coulomb's law, what we have studied just now. But before solving any question, we have to visualize this thing. And it is very interesting to visualize this question. And let me form a question in graphical representation, and then let us try to solve it. So what the question says, it says I have a charge Q1 that is plus Q, and it is at a distance d from the origin, and the second positive charge Q2 plus Q is located at the origin. So as you can see, I have a charge plus Q that is towards this direction, and another charge Q2 which is again plus Q, which is located at the origin. This is in y-axis. So this is y-axis as already given in the question. So this is the first part of the question. Then we have another part. There is a negative charge Q3 that is minus 2Q, and it is located on x-axis at a distance of 2d away from Q1. So please remember, this is the x-axis now. So we have formulated x and y-axis. So we have the charge Q3 minus 2Q, and the distance between Q1 and Q3 is 2d as it is in the question. So it says this is the scenario now. So this question, this is the graphical representation of the question, and it says I have to evaluate the net electrostatic force on Q1 due to the other two charges. So what we are going to see is what is the net amount of charge faced by Q1 due to Q2 and Q3. So this is the question, right? Now let us try to understand how we can calculate the force. We already have Coulomb's law, and we know that Coulomb's law gives you the understanding of force exerted by one charge over other. So I will try to solve this step by step. Please follow the entire step. It is very simple, and the same steps you can use when you do a larger problem or a different problem of different charges and different amount of distance. Okay. So let us see how the force will be. So this is the question we have formulated. We already have this equation from Coulomb's law. The Q1, Q2 are the charges. R12 is the distance. F12 is the force exerted by 2 on 1. So let us see how we can solve it. So this is the force F2 exerted by 2 on 1. So let us consider first Q1 and Q2. So force exerted by Q2 on Q1 will be F2. And similarly, force exerted by Q3 on Q1 will be F3. Now please remember, I have inverted the direction because this is negative and this is positive. So the net direction will be attraction. So towards it will be attracted towards this. And since minus 2q is larger than plus q, the attraction force will be towards the Q3 charge. So these are the two forces which will act. As you can see, F2 will be force due to Q2, F3 will be force due to Q3. These two forces are there. So what will be the net amount of force? The net amount of force acting on Q1 will be force due to charge 2 and charge 3. That will be the vector sum of F2 and F3. So what we can do, we can individually find out the value of F2 and F3. So F2, as you can see, we can directly write from our Coulomb's law that F2 equals to K Q1 Q2 upon R12 square, and J is J hat because it is in only y direction. So please remember these vectors I, J, K. I is for X, J is for Y, and K is for Z. Right now we don't have Z direction. It is a two-dimensional problem. So we use I and J. So you can see Q1, Q2. Q1 is plus Q. Q2 is plus Q. So I have kept the values of two charges as Q and Q. D is the distance between these two. So I have written as D square. And we can find out net force F2 because of charge 2 on 1. So this is the final value of F2, force exerted by Q2 over Q1. So this is F2. Now let us see what will be the value of F3, which is the force exerted on Q1 due to Q3. So if I have to write the force, now I can find out force and I can discretize the force into two elements, X component and Y component. As you can see, the F3 have X component and Y component. So I can write F3xi plus F3yj. So it has X component and Y component. F3x is X component of F3. F3y is Y component of F3. And theta is the angle which it makes with this particular x-axis. Okay. So I can straight away write it as F3x will be F3 cos theta and F3y will be F3 sin theta. Please remember, in this case, cos theta is in positive direction of x and this sin theta is in negative direction, and that's why this negative sign comes into picture. So we have F3 cos theta I for x component of F3, F3 sin theta j for y component. I pertains to x-axis, j pertains to y-axis. And negative sign comes because the direction is in negative y direction. So I can straight away write F3 is equivalent to K Q1 Q3 upon R13 square cos theta. Then K equals to Q1 Q3 upon R13 square. So you know value of Q1, Q3. Q1 is plus Q, Q3 is minus 2Q, and R1 is 2D, as you can see in the diagram. And we can also find out what will be the value of cos theta. So cos theta you can straight away find out from the figure. You can use the trigonometric function, and you will end up getting as sin theta equals to 1 by 2 and cos theta equals to root 3 by 2. So this is how you can find out values of cos theta, and it is very straight away from here. This you can write cos theta. Cos theta will be this upon hypotenuse, and sin theta will be this upon hypotenuse, and you can finally get this particular thing. So you got this. I will write F3 as in terms of sin theta and cos theta. I have the values. I have the value of charges. I have the value of distance. So F3 we will get it as Q1, which is plus Q, Q3, which is minus 2Q, and distance is 2D square, and cos theta is root 3 by 2, and sin theta is 1 by 2. Sin theta is 1 by 2. So it becomes plus Q minus 2Q upon 2D square. So we have two forces now, F2 and F3. What I will do, I can further simplify value of F3, and I will do the calculations. So we get it as F3 as 2K 2Q square upon 4D square root 3 by 2I minus K 2Q square upon 4D square 1 by 2J. And further simplification, you can get it F3 as this. So the net force, as we already have said, on Q1 due to Q2 and Q3 will be F2 plus F3. So as you can see, I have just added up these quantities, and I have got the final force as root 3 by 4 K Q square upon D square I plus 3 by 4 K Q square upon D square J. So you can highlight it, and that is your final answer. And this is the total amount of force exerted on Q1 due to Q2 and Q3. So any issues with this? I hope we have done the entire calculation step by step and concrete steps, and I hope you have understood it.
Yes.
Any questions with this calculation? Any questions with this?
No, sir.
No, no questions, right? So I hope now you understood that Coulomb's law can be used when we want to exert, when we need to find out force applied or exerted by one charge over other, right? And for finding out the total force experienced by a single charge, by multiple charge, you have to calculate the individual effect. And after calculating the individual effect, you can also find out, or you can use superposition theorem, and you can find out net amount of force felt by a particular charge. So that is very important, and you all must know how to calculate a particular force exerted on a charge, generally speaking point charges, by some other point charges. So this theory is very important, and I just want to demonstrate it, that how you can calculate the force exerted on a single point by some other forces which are surrounding. This question can be modified now. Instead of having two charges, I can have 5 or 7 charges of different values, of different orientation, but steps will be same. You need to analyze force individually between two elements or between two charges, and the final force will be a vector sum of all the forces exerted on a particular charge. So this type of questions and this type of calculations are very important, and this gives you the understanding of Coulomb's law, that how I can use Coulomb's law for finding out force exerted on a particular point. So I hope this thing is very clear. This is also known as application of Coulomb's law in real electromagnetics. Now, this question has some more thing to do. So once you have become an expert at problems like this, you can combine and perhaps even skip some steps. Why? What I say, you can skip some steps, but skipping steps on work to be graded is not recommended, because when we grade it for some students, then we need to have all the steps, because that is what marking system goes. So that is not mandatory for graduates and for other people who are doing calculations. But for undergraduate students, this is very important. They must denote point by point how they end up with that particular result. So your answer can be in vector notation as in the previous slide, or you may write in this form that fx and fy, so x component and y component separately you can write. That is also correct to write, but generally we write it as one, that force equals to fxj plus fxi plus fyj. That is also one form of writing. You can write in this form too, no issues with this. Now, another thing is your answer can also be as a magnitude and direction. That is also very true. You can do it. All three above ways of writing f completely specify the vector. So whatever your answer is, whatever the values you're getting, please write them in a complete fundamental notation. Otherwise, it becomes very difficult when professors grade those problems. So when we have to grade a problem, at that particular time, you have to be very sure that you have mentioned your results in a correct form. So I hope you have got this concept. Let's move to some other concepts. So this is the force, actual amount of force and the direction of force from what we have calculated. So we are talking about the same problem. We have three charges over here. And this is the force which is exerted by Q2 and Q3 over Q1. So the force exerted by Q2 over Q1 is in this direction. Force exerted by Q3 on Q1 is in this direction. And the resultant force, as we have already calculated in our previous calculation, that pertains to this particular direction. So I hope this is what we have already done. This is merely graphical representation of the force which we have found out in our previous question. Now there are some other twists in this question. Say, if Q1 were to free, or Q1 is free to move, what direction would its initial acceleration be? This is very important to address. And how would I calculate that acceleration? So the question is, if I have Q1, which is free to move in any direction, then what direction would its initial acceleration be? And how would I calculate that acceleration? That is very important. And students, professors, they must try to think that what will be the direction of this particular charge if it is freely moving, when it is moving in the force which is applied by Q2 and Q3 over Q1. So please try to analyze this concept and try to understand at what particular point this acceleration will be.
And it will move in the direction of resultant force.
Yes, correct. It will move in the direction of resultant force, and that is very true because I have already mentioned the direction of force. So it will go in that particular direction. And some other questions which could be entertained is, would the acceleration remain constant as Q1 moved? Could I use the equation of kinematics? Please remember from your class of physics to describe the motion of Q1. So I hope if you have got this concept, then you can rely on other concepts of physics and you can address these fundamental problems. That what could be acceleration of Q1, what will be the direction of motion, and all sorts of things. That I leave up to you all for the audience to think about and come up with some concrete answer, as someone has just answered about the direction of initial acceleration. So that was application of Coulomb's law. And I have explained you how or what amount of force will be exerted on a particular point charge because of other point charges located at a different location. If you have seen some GATE papers or GATE question papers, such type of questions they ask fundamentally. They ask that suppose there are some point charges, what will be force and what will be the direction of force, and these fundamental questions are generally asked in electromagnetics. So I hope such type of questions Well, you can entertain it and you can do those questions and you can find out net amount of force at a particular on a particular charge, and this could be done using Coulomb's law. So I hope I have explained you how Coulomb's law works and what are the permutations and combinations of Coulomb's law. So Coulomb's law is very clear. Any issues with the Coulomb's law? I hope there's none. People have understood it. I take it as granted that people have got whatever the concept I have explained. So the next point for today's agenda is electric field. And our understanding is, after understanding this topic, you must be able to calculate the force on a charged particle in an electric field. So that is what our understanding should be. If I know electric field, we must be able to calculate the force on a charged particle in an electric field. So let us see what is electric field and how we can define it. Right. So taking from the previous concept of Coulomb's law, you know this Coulomb's law says that force exerted between two charges can be derived using this formula. So we have F12, that is force exerted by 2 on 1, will be equivalent to 1 by 4 pi epsilon naught Q1 Q2 upon R1 T square. So this is Coulomb's law, but the question arises that how charge 2 knows that there is presence of charge Q1, or another way I can say, suppose there is already a charge Q1, and then how this will know that this force is coming from Q1. So explaining this principle, that how two charges comes to know that there is some sort of force, we have the introduction of the concept of electric field. Or we can say, how does a charged particle know there's another one is there? For this particular understanding, we introduce the concept of electric field, that Coulomb's law of force is nothing but an amount of electric field produced by that particular charge. Please remember this. So Coulomb's law is nothing but force produced by the charge, or when we have done the calculation of Coulomb's law, we say that force 1, 2, that is force on 1 because of 2 is given by this formula. Then this force is nothing but electric field exerted by charge 2 on 1 or charge 1 on 2. So this is what gives you the definition of electric field. So a charged particle creates an electric field in all space. That is what now our understanding is. Every charged particle, as I have said, this will exert some amount of force, and every charged particle, when it creates a field, that is known as electric field. Please remember, we are talking about stationary charges. I will come to the definition of magnetic field, because charges in motion produces magnetic field, but stationary charges produces electric. So I have a charged particle, suppose this is indicated as plus, then it will exert some amount of field, and I say these are electric field, and you can say this is the spreading of electric field. I will repeat it. This is charge, and you can see that this will spread electric field like this. And this is very interesting. I have explained you the concept of divergence. So electric fields are divergent in nature. As you can see, again I will show you, this is a charge, and these electric fields are coming out from the particular charge. So this is how electric field is generated, electric field are created because of point charges. So other charged particles senses the field and experiences a force in response. That is what we understand. So distinguishing source charges and test charges, what we do, we consider one particular charge as the source charge and another as unit charges or very small amount of charges that are known as test charges. Now let us see, I have indicated 2-3 charges. So generally, the direction of force or field is in the direction opposite to the charge, opposite to the positive charge. The direction of electric field is always emerging out of positive charge. That is what our understanding is. Okay. But sometimes, as you can see, this is a positive charge. So this will have the repulsive effect. But when it is negative charge, then there will be attraction effect. So I have given you an example where we have charges. Suppose if I have positive charge, source charge over here, and I have another test positive charge over here, then the force exerted by 1 on 2 will be in this particular direction, and force exerted by this on this will be in this direction. But since this is attractive in nature, direction of force will be towards. So I hope now you have got the concept of electric field also. So electric field is nothing but the force which we have experienced in Coulomb's law is nothing but electric fields. So let us see what is the definition of electric field. So it can be one or more source charges can be there. So the electric field can be explained in terms of point charges which is kept at a vicinity of the charge. So electric field is defined as F naught. Please remember, F naught is the force from the Coulomb upon Q, which is the charge which is kept near to that particular charge. So force can be written as Q into E. Q into E means Q is your test charge and E is the electric field. That is another definition of force, what we have got from here, that force is equivalent to Q into E. E is the electric field produced by the charge, and Q is the test charge which is placed to absorb that electric field. Now, if I say in terms of starting equations, this is your second starting equation. It is a vector equation that tells you magnitude and direction of the force. Please remember, our first starting equation was Coulomb's law, and we have derived something from the Coulomb's law. We say this is our second starting equation, and it is a vector equation that tells you magnitude and direction of the force. So that is very interesting. It gives you the concept of magnitude and direction of the force. Contrary to this, we can use Coulomb's law and still we can find out magnitude and force of the field. But it is always good to represent electric field in terms of force and in terms of unit charge. And I have given you the formula where force equals to QE. Q is the test charge and E is electric field. So let us say electric field, unit of electric field. It is in Newton per Coulomb, Newton for force and Coulomb for charge. Electric field can also be expressed in terms of volt per meter. I hope you all are familiar with these units. Now, electric field can exist independent of whether there is a charged particle around to feel it or not. That is very interesting. Even though, suppose if I don't have a test charge which is kept along the charge, even then that particular charged particle will produce some amount of force. That is very true when we say in terms of Coulomb's law. Even though if I don't have another particle to feel that charge, still we will always have some amount of electric field over there. So please remember this. This is very interesting. So a single charge can always produce some amount of force. That is what our understanding is. Okay. So remember, the electric field direction is the direction of positive charge. So this is what the direction of positive charge is. A positive charge will be repelled by another positive charge. That is what our understanding is. Therefore, the direction of electric field is always away from positive and towards negative. Please remember, this is how your direction of electric field will be. It will be always coming out from positive. So, as you can see in the animation, that electric fields are always generated from positive charge and they move away from positive charge. Since they are moving away from positive charge, they will go towards the negative charge. That is the analogy we understand from this particular diagram. So let me quickly, the gravitational poles, and I hope we have done. Okay. So it's already 12:30, and I hope we have covered a lot. We will We will start at this point tomorrow at 11 o'clock. So still people are there listening to me.
Yes, sir.
So I hope you would have got the concept of Coulomb's law. You have got the application of Coulomb's law. We have done electric field, orientation of electric field, direction of electric field, right? And then further concepts of electric field and other concepts we will study tomorrow. So any questions till this, what I have explained today?
No, sir.
No questions. I hope everything is very clear. So let's meet tomorrow at the same time at 11 o'clock. And we can discuss further concepts of electric fields and generation of electric fields.
Yes, sir.
Okay, then that's all from my side. If any questions are there, please go ahead with the questions. Otherwise, I shall be ending this meeting.
No, sir. Thank you, sir.
Yeah, please. Someone is saying something?
No, sir. No questions. Thank
No
you.
questions. I hope everything is great. Okay, then let's meet tomorrow at the same time at 11 o'clock.
Okay. Good day, sir.
Yep.